without problem. Yeah, right. So that's B8. So A3, molecular orbital diagrams. So molecular orbital diagrams, they are definitely daunting, I think, at first, but you do enough of them, and they all start having the exact same pattern, pretty much the exact same approach, right? There isn't really much that changes between them, except for when you start going to like heteronuclear diatomics, energies are slightly different on the two sides. But yeah, so in this case right here, right, we're going to draw the MO diagram for O2. And so the way that I always like to approach it is that I'll draw the atomic orbital energy diagrams on the two different sides of the paper, right? So I have one oxygen over here, right? And so I'm going to have my 2s, and then I'm going to have my 3p's, or not 3p's, my three times, what happened? Oh, my 3 times 2p orbitals, right? There's 3 2p orbitals that we have for each oxygen. And then over here, right, I'll draw my other one, right? So I'll have one oxygen here, and then again another 2s, and then the 3 2p orbitals in that case, right? So I have all of these guys. I fill them in with the number of electrons that I'm supposed to have, right? So oxygen has 6 valence electrons. So following the Aufbau principle, Hund's rule, and the Pauli exclusion principle, right? I'll have 1, 2, 3, 4, 5, 6 over here, right? 1, 2, 3, 4, 5, 6, right? So now all of the atomic orbital energy level diagrams are done. The next question is what happens to form the molecular orbitals, right? And so I'll draw the molecular orbitals in the middle of the two of them. And so first things first, right? The 2s's, they're going to be interacting with each other, right? In this case right here. And so because if we look at what each one of them looks like, right? So 2s is just simply, right? It's just simply a circle, right? And then for the p's, we have, right, the pz, px, py. And so then the same thing here. In these cases, right? And so looking at it, the two 2s's, when they're interacting with each other, they're going to form a sigma bond. And so the big definition difference, right, between sigma and pi bonds is nodes, right? So if you have along the bonding axis, if you have a node that goes there, right, then that's not a sigma bond, that's going to be a pi bond, right? So sigma bonds have no nodes along the bonding axis, right, which is why they look like that right there. And so this is a sigma bond, right? A sigma antibond then just simply has one node that is then perpendicular and cuts the bonding axis in half, right? So if this is the bonding axis right there. And then in terms of pi bonds, right, the pi bonding interaction is, kind of looks like a hamburger bun where, one side is shaded. And so in this case, right, you have a node that's along the bonding axis in that case that cuts the molecular orbital, in half. And then for the pi antibonding interaction, you still have, a node that's along the bonding axis, because it's off. The shading was different, wrong, right? You have that node that is still along the bonding axis, because again, it goes back to what the starting orbitals are, right? So p orbitals, right, have an angular node that's right there, right? And so that gets carried over into the pi bond in this case. And so you have, along the bonding axis, you have still that node, but then you also now have, again, right, a node that is is perpendicular. It cuts the MO, through the bonding, vector distance right there in those cases. And so those are the differences between all of them and how you can identify what type of orbital each one is. And so anytime you have a sigma bond, you automatically have to have a sigma antibonding orbital, right? So they go hand in hand with each other, because mathematically, right, if you're going to have constructive interference, right, positive interactions between the two of them, you also have to have a situation then where you have negative interference, right, where you're subtracting one from the other. And that's what happens in the antibonding scenario. And so they always go directly to each other. So in this case right here, right, for the 2s, what we'll get then is then a sigma bonding orbital that's going to be then below the starting orbitals in this case. And then we're also going to end up with a sigma antibonding orbital that's going to be above the 2s orbitals in this case, right? So that's the sigma antibonding right there, right? And I'm just going to draw lines to indicate where everything is coming from, right? And so, you know, those are done. And so this is the, you know, sigma bonding, right? This is the sigma anti-bonding right there. Just, you know, drawing what they look like. Next, we have the 2p's. And so in the case of the 2p's, right, we have two of the p orbitals that are going to be oriented towards each other, right? Those are going to be forming then the sigma bond in this case. Right? And then you're also going to have 2 pi bonding orbitals, right? Because those are going to be then, you know, basically next to each other, but they're going to interact together to make like the hamburger bun scenario. Now, the thing to pay attention to is which atoms you're using in these cases. And so, you know, looking at it, right, we're at O2. If you look at, you know, the textbook and everything, there's a very clear point where things split, right, in terms of what the ordering of the molecular orbitals is in a diatomic. And that split happens between nitrogen and oxygen, right? So oxygen follows the trend where what happens is that you have the sigma, you know, for the P's, that you have the sigma bonding orbital as the lowest one. And then after that, the 2 pi orbitals come, right? And then, you know, you have the pi anti-bonding and you have the sigma anti-bonding, right? And so that's what happens here in this case. And so that's just a thing that you know, easy enough just to remember, right? That's where that split happens. And so we'll talk about for a different problem, I think it's A4 in a second, right? Where that isn't the case. Right, but that right there is the, you know, the bare bones of our molecular orbital diagram. Now all we have to do is throw in our electrons. And so if we're going through, right, we have 6 electrons from this oxygen, we have 6 electrons from this oxygen. So we should have a total of 12 electrons that we fill in. And so we just fill it in, right, using, again, the Pauli exclusion principle, you know, Hund's rule, the Aufbau principle, and so forth. So if we go through, right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So we fill it all in, and that's what our MO diagram looks like, right? And it follows all those different rules. The most important thing to pay attention to, right, is that for the pi anti-bonding orbital, the electrons aren't paired up, right? They're in 2 separate orbitals. And that has to do with Hund's rule, right? Because you're trying to maximize the spin in that case. And so you don't fill a complete orbital if it's degenerate before you start putting some in the other one in those cases. And so that's what it looks like right there. And that's, you know, a very common mistake people do when they just like quickly rush through, especially when they start pairing up electrons, is that they don't do that part. And so, you know, paying attention to that and thinking about that and going through those steps, you know, slowly pays off a ton. Because what this shows is that oxygen is actually paramagnetic, right? But let me just continue to answer these questions, right? So which valence atomic orbitals combine to form sigma MOs and O2, draw the sigma overlap, right? So we've already looked at this kind of, right? So we have, you know, the 2S's in this case, those interact right here, right? And they form, you know, this sigma bond right there. And then you can also have, you know, the other combination where you're subtracting them from each other. And then in that case, right, what you get is the anti-bonding combination, right? So this is the sigma and this is the sigma anti-bond. Same thing, right, with the p orbitals, right? You're going to have one, right, these guys interacting with each other. And so what they'll do is form a sigma bond that looks something like this. And then you can also have the scenario, right, where they're subtracted from each other. And so in that case, right, what you get is something that looks kind of like this right here. Right, and so that's what the sigma bond or the sigma orbitals all look like in those cases. And then for the pi's, right, what you have is then the px scenario, right, where you have the px plus the px in this case, and so that makes the hamburger bun, right? But then you can also have the scenario where they're subtracting from each other, right? And that's where you get, you know, the weird dumbbell situation, right? And then same thing when, you know, these are the PXs, this is the PZ, and I'm just using, right, what I always do. So personal preference and the way that I was taught is that the, you know, the primary bonding axis is always going to be the z-axis in a system. But if you want to do what the textbook does, where it goes like px as the bonding axis, right? That's perfectly fine as long as you stay consistent. But yes, we have this, and then we go here, right? And so these are then the PYs. And so what you get is these combinations right here. So this is the pi, this is the pi star, right? So this is the PY. And so then what is the overall bond order? So if we go through, right, the way that you calculate the bond order is you add up all the electrons that are in bonding orbitals. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 in bonding orbiters, or sorry, bonding orbitals, right? So the bond order is equal to 8. And then we subtract out all the anti-bonding electrons. So we have 1, 2, 3, 4. So there's 4 here. And then we divide that number by 2. And so what we get in that case is going to be 2, right? Which makes sense. It matches what we have in our Lewis structure, right? If we draw the Lewis structure for O2, it looks like this right here, right? It tells us that we have a double bond. And so then E, right? How many electrons must be added to O2 to reduce the bond order to 0? If this number of electrons is added, what products will be formed? So if we go back and look at the MO diagram, in this case, right, what we can see to go to a bond order of 0, right, we have to add 4 more electrons. So if we do that, right, we would be adding, let me change the color here of these electrons, right? We would be adding those here and then right here, right? So we'd fill all of those electrons right there, right? So we would have 16 electrons. And so if we completely break the bonds, right, by having a bond order of 0, what we then have is essentially 2 different atoms then that are going to have 8 electrons. And so 8 electrons on each atom, right, is going to be then the O2 minus ion, right, is what it's going to form in that case, right? Because those have a full octet, right, 8 electrons in that case. And so that's what happens in those scenarios, right? That's how you break O2s. You just pump in 4 electrons and you get, oxide, right? You get O2 minus.